Server hardware fails, data sectors corrupt, malware encrypts files, and humans make mistakes. The threat landscape facing enterprise data infrastructure is constant and compounding. The primary objective of any data security strategy is to prevent permanent data loss, minimize system downtime, and ensure absolute business continuity when those failures occur. Achieving that continuity introduces a massive engineering constraint. We cannot simply copy a server's entire 50-terabyte drive every single day. The physical bottlenecks simply won't allow it. We are restricted by finite storage capacity on the target drives, limited network bandwidth to move the files, and the short timeframes, or backup windows, available to run the process without disrupting daily business operations. Because of these physical limits, guaranteeing data survival requires an optimized, intelligently architected system of redundancy, rather than just blindly copying everything. This infographic details backup timelines. We start with the baseline, the full backup. As the name implies, it copies every single piece of data. This is the simplest method, but demands the largest storage capacity. To solve that, we introduce the incremental backup. It captures only the specific data blocks changed since the last backup. This creates the smallest daily footprint and runs fastest, but creates the longest, riskiest recovery chain. While the incremental approach solves our daily storage constraints, it sacrifices critical recovery speed when a disaster strikes. That brings us to a middle ground solution, the differential backup. It captures all changes made since the last full backup, ignoring intervening backups. This requires moderate storage, but provides significantly faster recovery, only requiring the original full and most recent differential. Finally, for enterprise systems, we use the synthetic full backup. The system automatically combines an existing full backup with recent incrementals to reconstruct a new virtual full backup offline, saving live network bandwidth. Choosing the right backup chain is a calculated mathematical balance between preserving daily operational bandwidth and ensuring emergency recovery speed. Once those logical chains are chosen, they must be scheduled in a strict rotation. Without a rotation, these backups would scale infinitely and consume every available byte of storage. This diagram illustrates the GFS, or grandfather-father-son, backup scheme. At the pyramid's base is the Sun tier, daily short-term backups rapidly reused weekly. Moving up is the Father tier, weekly medium-term copies retained until replaced monthly. At the peak is the Grandfather tier, monthly long-term archives kept permanently or yearly to ensure major disaster recovery and legal compliance. The GFS scheme provides a highly structured, predictable set of temporal restore points, allowing you to cycle through history without requiring infinite physical hard drives. A perfectly scheduled backup chain is entirely useless if it is stored on the exact same physical drive that catches fire. This introduces the 3-2-1 rule. Maintain 3 copies of your data across 2 different media types with at least 1 copy stored off-site. When a failure occurs, the disaster's spatial location dictates our response. This diagram compares our main recovery vectors. On the left is in-place recovery, restoring data directly back to its original system. This method is ideal for resolving minor data loss or file corruption where the hardware is healthy. On the right is alternate location recovery, restoring data to different hardware or a new cloud site. This vector is mandatory for major physical disasters, enabling business continuity while original hardware is repaired. In short, while in-place recovery fixes broken files, alternate location recovery saves the entire business when the original infrastructure is gone. Organizations invest millions in this complex architecture because IT is bound by strict federal and international regulatory frameworks regarding data handling. Take PII, Personally Identifiable Information, strictly governed by EU GLBA and California CPRA. Next, PHI, Private Healthcare Information, is heavily protected under HIPAA, requiring anonymized handling. Finally, PCI, Payment Card Information, protects credit card and transaction records under PCI DSS standards. Because of these rigorous laws, best practices dictate that all backups must be encrypted both at rest and in transit, governed by least privilege access controls, and regularly tested in isolated sandbox environments. Data security requires the rigorous engineering of temporal, spatial, and logical redundancy to guarantee that an enterprise survives a catastrophic event intact.